Okay, so I was debating having you guys read it out of the textbook, but I'm kind of simplifying potential energy. And so I decided to just do a quick Edpuzzle to talk about just the key concepts about potential energy rather than have you read the section. It's got a lot of information. So we've talked so far about kinetic energy, which is the energy an object has when it has speed, right? The formula for kinetic energy is 1/2 mass times speed squared. We also have a different type of energy though, which is potential energy. We can think of potential energy, and the reason why it's called potential energy is it is the potential of an object to have kinetic energy. So it doesn't yet have kinetic energy because it's at rest. So whenever we are discussing an object's potential energy, it is only when it is at rest. Again, it's the potential to have kinetic energy. It does not yet have kinetic energy. So you won't ever be discussing an object's potential energy when it's in motion. That is specifically kinetic. Once more, potential energy is its potential to have kinetic energy. Are you okay? You want to come up? Come here. Come shoot with me. Yes, good boy. Okay, sit. Lay down. No, come back. Okay, he's right over there. That's fine. Anywho, so going on from here, you had a little moment to try and copy that stuff down. Now, we're going to talk about two types of potential energy. There's a couple different types, but these are the most common. And again, for right now, to kind of wrap up this semester, this quarter, I'm simplifying it, and then we're going to come back to this after fall break. So the two types we're going to be talking about here are gravitational potential energy and spring potential energy. These two will be on the test, but they're going to be very simple questions we're going to be talking about. Like I said, after fall break, we'll come back to potential energy. There's a lot more we can do with it. Okay, let's talk about gravitational potential energy. So this should make sense if, again, potential energy is the potential of an object to have kinetic energy. The higher an object is off the ground, the greater gravitational potential energy it has, and something that's closer. The formula for gravitational potential energy is just mgh. That's it. Mass times gravity, right, 10, times the height it is off the ground. That's what h stands for, the height off the ground. And again, this should make sense because as we continue to raise an object up, the gravitational potential energy will increase because the higher we go, when we drop it, when we actually do let it go, we will end up with a greater final kinetic energy. The greater the distance off the ground, the longer it has to travel, the more opportunity it has to speed up, right? If I'm really close to the ground, I just go, that object doesn't have a lot of opportunity to speed up. So it doesn't have a lot of potential for a lot of energy. Again, if you want to think about energy and work as if I dropped this thing on me, or if I collided with this thing, is it gonna hurt? That's kinetic energy, that's work, right? So if I drop an object on you right here, it doesn't have a lot of potential to hurt you. The higher I bring an object up, the more potential it has to hurt you because it's going to have a greater kinetic energy when it does hit you. So again, gravitational potential energy is just mass times gravity times the height. The greater the height, the greater potential to have, again, a high kinetic energy to have a lot of work done. So this is a real quick, easy example here. You hold a ball, mass 5 kilograms, above your head at a height of 1.5 meters above the ground. What potential energy does the ball have? So again, the ball is not moving. You're just holding it, but we can talk about its potential. So super easy. Potential energy of gravity. Whoops. Use my finger here. Equals mgh. That's it. Go ahead and take a moment and plug it in. So we have 5 for the mass, gravity is 10, and the height is 1.5. I will say, because these questions are so easy, do make sure your units are correct. This is meters, good to go. This is kilograms, good to go. It's possible that we're going to have to do some conversions. Remember, we always have to have kilograms meters, and seconds as our units, unless they say otherwise. So 50 times 1.5, that should be 75, right? And once again, we're talking about energy. The units here are still joules. So this is the potential energy this object can have if we were to drop it. Again, that's as far as we're going to be going right now. When we come back from fall break, we'll delve deeper into what this really means. Now let's do one more little question here, but this one's also pretty simple, just kind of applying our formula. Say on a different planet. On a different planet, gravity is different, right? So the potential energy this ball has at this same height is now 95 joules. So it has a greater potential energy, right? We said it was 75 joules here. On this planet, it's got a greater potential energy. What do you think that means to start with about the gravity on this planet? Is it greater than ours or smaller than ours? It's greater, right? If I hold an object at the same height with the same mass, but it has a greater potential energy, that means the gravity is going to be greater. So here's our formula. We are looking for what is the gravity on this planet then? We still have the same mass. We still have the same height. We're looking for the gravity. Go ahead and give that one a shot. And again, this is the current potential energy on this planet. So all you got to do is plug in what we know and solve for what we don't. This is the potential energy on this planet. It's a mass of 5. We're looking for the gravity on this planet, and the height is still 1.5. So all we got to do is get g by itself. We've got 5 times 1.5 is 7.5. Why did I put a decimal there? Ignore that. Divide by 7.5. So the acceleration due to gravity on this planet is 95 divided by 7.5, which is 12.7. So yes, our prediction was true. The gravity on this planet is going to be greater. It's probably a bigger planet. In fact, it has to be a bigger planet for the gravity to be bigger. So it has greater potential energy on this planet, since that acceleration is going to speed it up even more. When it hits the ground, it's going to have a higher velocity than it would on Earth. Now let's talk about springs. So I'm going to introduce Hooke's law here. All you need to do is copy this down. We're going to come back to Hooke's law, like I was saying, after fall break. So with springs also have a lot of potential to do work, right? We can compress a string or we can expand a spring, depending on the way it's coiled. And we can just kind of hold it there. And we feel the tension, right? We're like feeling it. When we let it go, then it converts to kinetic energy. But we can feel that potential, right? If you've ever expanded a string before, compressed it, you feel that potential, but once you let go, something's going to happen. Now, the force exerts on something, say if we had something attached to the end of the spring, depends on the attributes of that spring, such as how tightly it's coiled, how stiff it is, the material of the spring, etc. So this is Hooke's law. This is the force that a spring would exert on an object, which is what, this is not static friction, be careful here. If you see this formula, and it has a little s here, that's spring, yeah. So Hooke was a guy who figured this out about springs. That again, this would be the force they exert on something. So let's go ahead and fill in what these variables are. K is the spring constant for that particular spring. So again, depending on how tightly that spring is coiled, how stiff it is, that's going to be particular to that spring. That's what K is. Now what X is the displacement from the spring's equilibrium position. Again, pause as needed to copy. What this means is basically how far did you compress it or how far did you stretch it? For example, if this spring is in its equilibrium position, equilibrium just means if I'm sitting there, I'm not doing anything to it, it's just there, right? That's its equilibrium position. Would I, sorry, let me actually say this. This one is a spring that I could compress or stretch, right? If this is its equilibrium position, I could compress it a distance, or we could stretch it actually too. This one would probably be very hard to stretch, but we could do that. So this could, X is referring to, say that normally it's 10 centimeters long, and I've compressed it to 8 centimeters. That's 2 centimeters difference. That's what this is talking about. Displacement from the spring's equilibrium position. If 10 centimeters is equilibrium and I've compressed it to 8, that's 2 centimeters displacement. Now this is also a spring that we would stretch, right? I can't compress this string, but we could stretch it. So same thing, if we say that this spring normally from here to here is 5 centimeters, and I have stretched it to 9 centimeters. It's originally 5, I've stretched it to 9. What's that displacement? 4, right? That would be the X. Sometimes they tell you it's displaced 4 centimeters. Sometimes they tell you equilibrium is 5, I stretched it to 9. That's a displacement of 4 centimeters. Again, we're not really going to do much with Hooke's law yet, but I just wanted to introduce this as we introduce springs. What we really are going to talk about is the potential energy of these springs. I'm going to keep saying strings, oh my gosh. So again, you know that when you compress or stretch a string, you feel that tension, it just wants to go. That's the potential energy, right? When we let it go, we can apply that force, we can have that kinetic energy. And you should know that, again, the more you compress or the more you stretch, that the greater tension you feel, and you know it's going to do much more work, you know it's going to have a lot more kinetic energy. So the potential energy for a spring looks actually like the formula for kinetic energy, just for any object. This is 1/2 K, that constant we just talked about, times X squared. Remember, X is how far it is compressed from its equilibrium, compressed or stretched. So like I said, the questions are going to be very simple. We'll do a couple extra in class. But this question says, what is the potential energy of a spring? So potential energy of a spring is 1/2 K, it's constant, times X squared, its displacement from its equilibrium. It has a spring constant of 400 and it is compressed 5 centimeters from its equilibrium. So because these questions are so easy, guys, again, you're not going to have a lot of, this will be about as hard as it gets. The only thing we got to be careful of, which I mentioned before, is most of the time, springs are very small. A lot of times we're dealing with very small springs. Sometimes if you're looking at a semi-truck or a tractor, the springs for their suspension are massive. They're huge, they're thick, and they're a lot bigger. Most of the time, though, if we're talking about springs, we're talking about very small things. This still needs to be in meters because potential energy is measured in joules, and in order to get a joule, we need meters. So that's the only difficult thing you'll have to do here, is make sure you keep an eye out for those conversions. So take a moment, actually, I went ahead and start plugging it in. Plug in your K, your spring constant, convert 5 centimeters to meters, and then pop it in. There's your answer. Okay, so K is 400. So 5 centimeters to meters. Careful with this. In 1 meter, there is 100 centimeters. So 5 divided by 100, you should have gotten 0.05. So the potential energy of this spring is 200 times 0.05. What is that going to be? Like 10? That's correct. 10 joules. That is going to relate to the kinetic energy it will release when we release the spring. But we'll talk more about that after fall break. Right now, this is as hard as it's going to get for potential energy. We'll come back to it after fall break.